Okay, we're going to take a look at a heating vat. So what we have here is a fluid is coming in with a given temperature and a given flow rate, volumetric flow rate, and it's coming into this tank. It's being mixed, so we will assume there's a uniform temperature through the tank, and so this is causing the mixing of basically the heat with the material. We have here's heat being applied because we want to heat this thing up. The tank will have a characteristic volume. The fluid will have a characteristic density and specific heat. The walls are insulated, but they're not perfectly insulated, so there is heat flow out through the walls, and that is regulated by this R value. And then as stuff heats up, it then goes outside the back end, so that'll have some characteristic temperature and the same flow rate as which the material arrived. Okay, so this is a tank. Heat is being put in and stored here as material comes in. So we're modeling this as a capacitor. So C times theta dot, okay, equals heat in minus heat out. Okay, now at steady state, as everything gets to gets to a certain temperature and stuff comes in here and goes out at the same temperature, in time, you would expect the temperature in the tank to remain basically constant. So you would wind up having heat in equals heat out because theta dot should become 0. Anyway, so capacitance is for the material inside, the density, the volume, times the specific heat. All right? So heat coming in. So we have heat coming in from two sources. We have our heat source right here. So that's whatever that is, QH of T. And then you have the heat value coming in from the flow. So that's going to be the temperature times the mass flow rate, which is volumetric flow rate times density times specific heat. So there's heat coming in. And you have heat coming out, treating that as a resistor. So you have the R values of the wall, 1 over R, theta minus theta A, driving the heat out. And then you have the heat and the flow coming out. Okay. Again, mass flow rate, there's these two terms, specific heat and temperature. And there, pretty much you have it. The rest is really just algebra. We go C theta dot equals heat in minus heat out. That's what we have here. Then I'm gathering terms. Here's all the thetas. Okay. Not including theta I, but this is the temperature of the tank. So we'd like to be able to, the purpose of this is to be able to model the temperature of the tank. So here we're gathering these things. And so now I'll divide through by that C here. And so here I've got temperature in the tank. So here's the differential equation in here. Equals 1 on C, the heat supplied, W on V, or omega on V, fluid input temperature, and then we have the resistive loss to the atmosphere. All right. If we use Laplace, okay, so we're going to convert this here into Laplace, and so we would have S plus these terms, and we could factor out a theta of S. Well, this is first order, so this will be 1 on the time constant. And so rather than write all this stuff, I'm going to just call this 1 on the time constant, which I'm noting here. All right. And if I do that, and so I divide all this through to the other side, we have 1 over C, S plus 1 on tau, you know what that is, QH, relative to the heat supplied. This is affecting the heat in this vat. All right, then you have the heat that is supplied by the flow, and it adjusts the heat in the vat according to this transfer function. And then you have the heat that's outside, and that adjusts the heat according to this transfer function. And there we have, oops, no, that's a plus. And that's all of them. And that completes this problem. We have one more to do. Talk to you then.